Hi everyone, my name is Chen. I'm a PhD student in the University of Queensland. I'll now present our paper, Semantics Disentangling for Generalized Zero-Shot Learning. Human beings have a remarkable ability to learn new concepts based on prior knowledge without seeing them before. For example, given the clues that the zebras look like horses, but with black and white stripes, one can quickly recognize a zebra if seen horses before. However, unlike humans, supervised machine learning algorithms can only classify samples belonging to the classes appeared during the training stage, and they are not able to handle unseen categories. This challenge motivates the study of zero-shot learning. Existing zero-shot learning techniques can be grouped into two types, embedding-based and generative-based. And our paper focuses on the generative-based, which learns a visual generator for the unseen classes based on the seen samples and the semantic representations of all classes. Most existing approaches directly leverage the visual features extracted from pre-trained deep models, which are not tailored for zero-shot learning tasks. From this figure, we can see that not all the dimensions of the extracted visual features are semantically related to the predefined attributes, which triggers the bias on learning semantic visual alignment and causes negative transfer to unseen classes. Despite an animal ears are visually salient in discriminating image samples, it is ignored in the manually annotated attributes. When generalizing to unseen classes, such as cats, it is easy to misclassify tigers because the visual features corresponding to the concepts big, strong, and muscle are not highlighted. From this case, we believe that zero-shot learning will benefit from using the visual features that can consistently align with respective semantic attributes. We define the type of visual features as the semantic consistent features, which are agnostic to both seen and unseen classes. In contrast, those visual features that are irrelevant to manually annotated attributes are defined as semantic unrelated. To unravel semantic consistent and semantic unrelated visual features from the original visual space, we propose a novel feature disentangling framework to disentangle the underlying information of visual features into two latent representations that are semantic consistent and semantic unrelated respectively. It can substantially increase the performance in zero-shot learning comparing to directly using entangled visual features. To facilitate the feature disentanglement by introducing a total correlation penalty in our framework, we arrive at a more accurate characterization of the semantically annotated attributes. Here is an illustration of our proposed method, which is comprised of a feature extraction backbone, a conditional VAE model for visual feature generation, and the disentangling modules to learn the two factorized latent representations. Comparing with the recent methods, our proposed method achieves state-of-the-art performance. In the right figure, we show the performance comparison between HS, HN, and H. From the observation on all datasets, semantic unrelated features HN performs much worse than the original latent feature H, which proves the ineffectiveness of HN in generalized zero-shot learning. In contrast, using semantic consistent features HS can further improve the performance, which validates the significant impact of HS. We visualize semantic consistent representations as HS and the semantic unrelated representations HN. Clearly, as we expected, the semantic consistent representations HS is much more discriminative than the semantic unrelated representation HN. However, we can still see discriminative patterns from HN as there are remaining discriminative features even if they are semantically unrelated. We conduct the image retrieval task to illustrate the qualitative results of the proposed method. We compare our proposed method with the base generative model CVAE when retrieving 100%, 50%, and 25% of the images from all the unseen classes. It can be seen that the disentangling module can significantly boost the retrieval performance among all settings. And the right-hand side figure illustrates the retrieved examples on the AWA datasets. The class name is given on top, following by the top three true positive retrieved images with green boxes and the top three false positive retrieved examples with red boxes. It can be seen that all false positive images look very similar to the ground truth examples. Thank you for listening. Any questions?